My name is Srini Seetharaman. I am an architect at Infinera. I am also an Open Daylight ambassador. I've been using Open Daylight for the past 4 years, and finally, I'm happy to say that in Infinera, I managed to actually get an SDN product out into the world, deployed in production with a customer, and it has been a pretty tough journey. So most of today's talk is I'm going to spend about half the talk about the transport networks and the challenges there, and what are the use cases that are most interesting for end users. And then I'll also spend the remaining half of the talk on our implementation of what we built and what lessons we learned from it while architecting for it. So, if you're hoping to learn mostly only about transport networks, you may be disappointed because I am going to go more into Open Daylight stuff as well. So, I was fairly new to the transport world, so I think it will help most of us to just get in the same page in case you're not from the transport world. So, in the past, most of you are familiar with the packet side. It's connectionless, best effort. You have a distributed control plane that does routing protocols and programs rules and things like that. The transport networks is kind of a term that has been floating around more recently, and it combines all the different connection-oriented services that you would see, which doesn't necessarily have to be just optical. It could be layer 0, layer 1, or layer 2. It could be even MPLS-based circuits. So the transport networks are typically circuit-oriented, and they have been coming up from the service provider side, mostly from the service provider networks. And going forward, more and more of the optical networks are also getting pretty programmable, and there's a lot of ways in which you can set the rates to be more flexible. And traditionally, they have been managed by AMS and NMS systems, but now with SDN coming in, there's a lot more room for programmable management of the whole network and the services. Even though there are standard protocols, there's definitely a move towards using SDN and having standardized Yang models and things like that. So if this is kind of the big picture of the different kind of networks you would have and different value props of use cases that we've been seeing, like SD-WAN, CORD, and things like that. There are a lot of transport SDN use cases that are available that people have been talking about. The simplest of that is bandwidth on demand or dynamic bandwidth. And of course, there are more on virtualization and network slicing. So I'm going to talk about some of those use cases. But definitely the evolution of the transport networks has been pretty slow. That's because they were kind of late to the whole SDN side. Most transport players just thought of OpenFlow and SDN as just something for the packet networks and just layer 2 and above. So there was definitely a late migration or late progression to SDN. So the benefits are kind of the same. With what you would get out of SDN, you would get agility, you would get more visibility into the networks. You would also be able to get faster time to market for all your applications and use cases. So the SDN value props are still the same for transport networks, but the exact APIs and how you would model your network and things like that are slightly different. So here are some of the transport centric use cases that we've been targeting. These are the ones we publicly talked about, but there are a few other applications that our customers seem very interested to build on their own. And so what we did was we took Open Daylight, and pretty much the things from Open Daylight we use are the RESTconf, NetConf, the MD-SAL, and clustering. And beyond that, most other things we ended up having to build on our own because the projects were either not as mature or what work we needed to do was significantly, or at least the customization we had to do was significant that it made more sense to just build it downstream. So we've actually been mostly freeloaded and not contributed as much. We've been giving a lot of bug reports and feedback and building the community, and we've been using some of these features, and we are planning to work with some of the new upcoming projects on transport PCE to upstream some of our ideas. But at this point, what we have is mostly downstream. So we have a whole layer of applications which can be installed dynamically on the fly, like instant virtual network, which is basically network virtualization, or dynamic bandwidth, which is same as bandwidth on demand. And these applications ride on top of an open API that is exposed by our SDN platform. And SDN platform not only includes the SDN controller, but also includes other microservices that we built on our own. Examples of microservices include constraint shortest path first algorithm, or CSPF, or even our own PCE layer. So all of those are microservices that are external to the JVM, but we integrate with that using some kind of a message bus. And on the Southbound, we have a device abstraction layer for programming our devices. So if you're familiar with transport networks, you would know that most networks are typically running some kind of a GMPLS and talking to each other. So there is a control plane in the underlying data plane, and our goal was to work with that control plane and program that and tweak the appropriate knobs to be able to get whatever we need. So we were actually not trying to completely dumb down our boxes, but kind of work in the middle ground. And of course, on our platform, the end users and the customers and other folks can also build their own applications, and they could also integrate other third-party microservices, or they could deploy other vendor devices as long as the plugin for that is available. For instance, a few months ago, we demonstrated a multi-layer use case of L2 VPN service, where we partnered with Corsa, which is a open flow switch, and we demonstrated how a Corsa box that has a L2 and L3 pipeline could be integrated with a L1 device like the Infinera CX to be able to provide an end-to-end L2 VPN. So this is something we demonstrated, and that was done again using an open daylight controller platform with our application that was doing the L2 VPN logic. So you could integrate how many ever different devices as long as the plugins for that are also included to support whatever device abstraction that we have built in. So the main use cases are as follows. The two I'm going to talk about today are the dynamic bandwidth, which is the L1 bandwidth on demand, where end user typically, typically in the past, end users will have to interface with an NMS system or with TL1 or some low-level APIs to be able to program, to be able to configure underlying devices. Instead of doing that, we expose a network-wide view for an end user to specify exactly what resources they want to allocate, and also be able to add certain calendaring along with that. So that a user can say at time XYZ, I want this much bandwidth between these two endpoints. And appropriately that can change. And here is where we initially looked at the intent project, but we've actually not used that. We built something on our own, and we're trying to kind of extend that to make it more similar to the intent concepts that most people talk about. But at this point, it is not using the network intent composition project. So the dynamic bandwidth application works both on layer 1 and layer 2. So this is where a lot of the transport network challenges come in, because the network tends to be multi-layer. If I look at open flow based networks, if I were to ask you which layer it is, you would say it's layerless, which is the right way, because each device you can program rules into it for layer 2 or layer 3 or whatever you want. But in when you have these existing control planes in the underlying data plane, along with the underlying data plane, there is a very clear division of labor on what each device is doing and what layer it's working in. And there's also a concept of affinity towards a certain underlying layer device. So when these cross-layer affinity is there, the way in which the bandwidth calendaring and the bandwidth allocation is done is a little bit different. So this was one of the challenges that our customers had on how to bring in a bandwidth calendaring while being layer aware, and that was the first application that we built. And the second application we built was a network virtualization or network slicing. I'm sure most of you would have heard of FlowVisor, which was a network slicing feature from like almost 5 years ago, which Big Switch and Stanford came up with. The concepts are fairly similar. It's just that this was never really brought into the multi-layer view. So what we did was to bring in a multi-layer virtualization so that a provider, like say for instance Level 3, who's a optical network provider who leases fiber and bandwidth to different customers, can potentially virtualize their network into multiple slices and provide that slice to their customers, so that their customers can look at their own individual virtual networks and manage resources within that without having to step on each other. And this significantly reduces the time for provisioning services, because now the end users are empowered to manage their own network and they don't have to wait on the service provider. So this this network slicing is very powerful, and we did that using also on the ODL Open Daylight platform. And for all of these, if you can think of, the earlier example, the bandwidth on demand and the network virtualization, for both of these we use IETF network models, and I'll talk about that a little later. So in these cases, the user can come and create a network or a slice of a network, and appropriately also create in the AAA different domains in Open Daylight and allocate different roles and policies for different domains and allocate that to the end user. So this is how we manage to implement and have the network virtualization and slicing feature implemented on top of our SDN platform. And this application will manage our underlying control plane to get the slicing that we need. So these are the top use cases that many of our customers wanted, and they've been wanting this for many years. It's just that with SDN now you have a better and easier programmability layer and a more standardized northbound API that you can expose. And now the end user can configure the whole system using netconf or sconf, and they are using standard IETF models for managing the whole application and underlying infrastructure. So these are the two main use cases that we used. And for doing that, the underlying pieces inside the controller platform are these blocks I've shown. I don't have time to go into each of these. I'm happy to talk to you after this during the break. But essentially, the main points I want to point out are that we have some standard blocks here. Some of these we were able to reuse, like the security, we used the AAA feature from Open Daylight. And for the inventory and topology management, unfortunately, we had to build something on our own because it is going to be using the IETF network and not the Open Daylight inventory or the network topology that OpenFlow plugin uses in Open Daylight. And for logging, there is a lot of toolkits in the JVM that Karaf has, and so we were able to use that. And for statistics and policy, we had to build something on our own. So the core, the kernel of our controller platform is Open Daylight, MDSAL, with the clustering and other features, but we had to build a lot of support around it. And then we had to build another whole layer of toolkits and orchestration to be able to install applications on the fly and to be able to upgrade and be able to backup, restore, and things like that. So even though, you have an open source platform like Open Daylight, which is actually now a lot more usable with Beryllium SR3, we still need to build a lot more applications and toolkits to make it really production ready. And our device abstraction layer is based on something called as the Open Transport Switch, which is which has a model which is based on a model of the OTWG, which is from ONF, the Optical Transport Working Group. So the ONF OTWG group provided the models on which our OTS is based on, but on the northbound of our controller platform, what we expose is IETF models. So we have different models here, and appropriate adaptation is done in the controller platform. So now I'd like to focus on some of the platform features. So these are the four main blocks: the northbound, the core or the service layer, and then the device layer along with the southbound. And our release was based on Beryllium SR3. And Beryllium SR3 compared to, I don't know if, so I've personally in the past 4 years, I've been experimenting and benchmarking and trying out releases starting all the way from hydrogen. And I would say that Beryllium SR3 is fairly stable and usable. And we've been also running this in a pilot deployment for several months, and it's been doing quite well. And we use, like I said, IETF models on the northbound. We use the IETF network and IETF transport TE as the two models. So the first one is for the discovery and for the tracking of the inventory, the nodes, links, networks, and things like that. The second one is for tracking the services. The transport TE is specifically focused on creating tunnels, point-to-point, multi-point tunnels. So we use the IETF transport TE. And we use the HA, which is from ODL clustering, but we are using something fairly simplistic. We are using the case where just one instance is an active controller while the other two are standby. So basically, we use the entity ownership service where the entity is just controller. This is kind of similar to what OVSDB and other platforms do, just that in those cases they are focused on the entity being the node, while we are just having one instance be the active controller for the whole system. Because we realize that even with active standby, there are several challenges to undertake and to ensure that there is clear fidelity in service creation, and there is clear tracing of exactly what happened in the network, debugging, troubleshooting. So there were several challenges here, because of which we actually have not taken the step to go to an active setup. And on the southbound, we use the open transport switch, like I mentioned. The reason being that transport networks already have a control plane that have a lot of programmable knobs. And OpenFlow 1.3 specifically was very oriented towards packet services and not multi-layer transport. So we ended up going the path of having our own API, which is based on the OTWG. And one of the interesting things to note is that in the case of OpenFlow plugin and also with the OpenFlow we've been noticing that the network is not a first-class entity, but it's a node. So most of these behave at node level, while transport networks work at a network level. What I mean is that if, let's say, I could have three, in the example I have here it says, it's probably not very clear, it says Ethernet OTN, which stands for Optical Transport Network, WDM, which is Wavelength Division Multiplexing. So it's layer 2, layer 1, layer 0. And here's the infrastructure, is the physical one. So each of these are different networks. So I can have a different name for these, and I can put them in different network containers. But in the case of the OpenFlow plugin or the Open Daylight inventory, there is just one catch-all network you put everything into. So it wasn't appropriate for us. So we had to build a custom Southbound plugin called the Open Transport Switch plugin. And that one basically allows you to have multiple networks and having cross-layer association using this concept called as a supporting node. And then we could also create different networks at each layer for different customers' own virtual network. And let's say one of the links were to break, let's say, I don't know, here, this link were to break and you have two different network partition, then each of that will also be different networks. So we realized that network is a first-class entity in transport networks. So we had to go with our own plugin, and we used the IETF network as the northbound facing model. So the main feature of the platform is to do, using the southbound, do discovery. And here is the IETF network, that network model. I've kind of put ... for the other attributes, but basically the main attributes is that you have a container called networks, inside which there is a list of network. And inside each network, you have a network ID and a list of links and a list of nodes. Inside each node, you have a list of termination points. So if you looked at the network-topology module in Open Daylight, it's kind of similar, but it has been expanded to have an external container called networks, so that you can actually get the whole list of networks here. So this is the model for the IETF network. I don't have the model for the IETF transport TE in the slide, but basically that has a top level container called TE, which is stands for traffic engineering, and inside that there is a container called tunnels, which stands for the list of all the different services that are created. So one of the other things we noticed, which is interesting in the transport network case, is that service creation typically takes a longer than a few seconds. So it is not, the right approach was not to have any REST or programming or RPC call hanging in there. We didn't want to have synchronous calls. Instead, what we did was whenever a user issues a new service creation, we just take the configuration and say, okay, thank you, we got the information, and we create some placeholder tunnel identifier. But then in the background, we start going about creating the service. And once the service is created, you will see a service show up on the operational store. So whenever a user creates a service, it's put in the config store, and then the Southbound plugin goes and programs the underlying devices. And when the programming is complete, a new service is discovered and put in the operational store. And that's the only way to know if it has actually been programmed on the underlying device. If let's say it didn't get programmed, if it's a success, then yeah, we have some extra flags in the config store saying success. But if it failed, we have some additional flags that says failure and also say exactly why that service creation failed. So we had to add a little bit more instrumentation to kind of track the life cycle. What we really wanted, which we didn't have, which we are working towards building for the next release, is a resource manager and a workflow tracker. If you guys are familiar with ONOS has something similar to that. Unfortunately, the NIC project has not yet caught up on that front. So we're doing something more custom, but we are hoping to expand this to have something more concrete and have a clear state machine behind this. So this is how we manage our services. And with regards to Northbound, we don't do anything special. We basically leverage whatever Open Daylight provides. We use REST, netconf. We have the basic and the bearer authentication. There is also some level of multi-tenanted user management, but there is some caveats in that. Unfortunately, the Shiro filtering is not as easy to work with on the RPC call RESTconf. So these are some feedback that we've given back to the REST netconf community. And the notifications, towards the end of the SR3, we ended up really fixing some bugs which has been upstreamed, and so WebSockets actually works now for Yang-based notifications, and of course there is Swagger for all the API documentations on the Northbound. And we built our own UI because it seemed to make a lot more sense to have it more customized to our Infinera branding. I'm not going to go into this, but our applications leverage significantly the akka and the domain-driven actor model. And Open Daylight, as you already know, the clustering and MDSAL already uses akka significantly. So the domain-driven model was very helpful for us in making our whole programming practice and our whole software development object-oriented, so that we can keep the behavior and the data as close to each other as possible. So all our service management was based on akka and the domain-driven actor model. We also architected for scaling across a larger network. If you know, most of these transport networks, they all deploy over thousands of miles. Even there are transcontinental cables and things like that. So we want deployments that can scale geographically and also with the number of nodes. So the best way we realized is to basically have a root leaf approach, so that you have some kind of a global orchestrator to which the end user will provide all the configuration, but all the real programming and the horsework and all the dirty work is done by the underlying leaf controllers that are deployed in multiple sites. And each of these leaf controller is actually a cluster of its own. So you can see here I have 3 JVMs here in the leaf, and I have 3 JVMs in the root, and they all talk to each other using some kind of a distributed message bus. So this is how we make it scale in a geographical sense. And one of the other points I want to point out is that the configuration data trickles downwards, southbound, while the operational data goes northbound. So we ensure that the user has to only interact with the root or the global controller, but all the programming is done on the leaf. Yeah, I'm not going to go into this. So yeah, as a summary or concluding remarks, I want to say that we definitely leverage the ODL platform significantly. All our interfaces are Yang based and open APIs, but we had to build a large number of other software pieces to make it production ready. We went into several architectural questions, especially on should we use ODL clustering. I mean, we've noticed some problems in ODL clustering also in switchovers and certain cases where leader election fails. So there are certain open bugs still. So we debated quite a bit on should we use the open delay clustering or should we build our own using some distributed data stores like HCD. And we also debated on should we use ODL WebSockets or should we build our own using Kafka. We also debated on using should we use routed RPC or should we use OSGI based routing. So we right now still use ODL clustering. We use ODL WebSockets. We don't use routed RPC, but we use OSGI. So we made some architectural choices, but of course all these evolve. So the goal is to build a platform because you don't know what applications are going to be there 5 years down the line. So the platform should be flexible and be able to support several different architectural choices, and that's what we want. We want something that's like flexible and you can adapt accordingly. And there are still some open concerns which I think have been brought up in other forums and other sessions. Upgrade, especially for the northbound REST API, is unclear. It's not backward compatible, so that's still open. The cluster management in Beryllium was very static using config files, and hopefully that'll. I have not checked Boron, but I'm hoping it'll get solved at least by Carbon. So these are some of the open issues. But yeah, building a solution for managing and controlling transport networks has been interesting. There are issues you have to face to customize it to the transport networks, but there are also issues with regards to bringing things into production. So if you have any questions, I'm happy to chat. I'll be around if you have any other discussions on these lines. I'm happy to discuss more. Yeah.
Yeah, curious question. Since you talk about your root controller high availability, how are you guys dealing with the root controller for geo-divergent scenario?
Sorry.
Your root controller geo-divergent. It's multi-site kind of thing.
Right now, we did not plan for that. I think at the end, basically what we learned was that often customers also have a layer of orchestration on top of that. So we've at this point just made them co-located with their own orchestrators. So like I said, these all plug into a message bus. So they're all in a message bus where there are certain roles identified on who's what. So it is possible to run multiple root controller clusters, but we've not explored that. Good question. Yeah.
You talked about microservices. So how do they interact with the OpenDaylight instance?
So right now we just have a plugin. So anything, plugin is what you would use to interface with anything external to the JVM. So we have a Docker plugin that we wrote, which basically will integrate with spawning and creating the micro instance. And once it's brought up, we have an external message bus for, again, the microservice to interact with the rest of the system. And we have some proxy and some adapters that we built specifically for interfacing with the microservices.
So, but you said message bus, right? And if you want to do path computation, that's what you are doing in the microservices.
That's correct.
Do you need all the data to do the path computation? Like, do you transfer the data across the message bus? Or
At this point, yeah, we do that, yeah.
It's not externally hosted parallelly?
No, at this point, because our authoritative data store is our OpenDaylight data store at the root, we kind of
Still MD server?
It's still MD service. Yeah, but we are exploring the HCD as an alternative, and I think there was either in the developer forum there's a session on. Yeah. Cool. Thanks, guys.